Hi and welcome to Easy A Tutoring. In this video, we will be looking at how to calculate the percentage yield from an experimental yield. So what is a percentage yield? Well, this is the ratio of the actual yield to the theoretical yield expressed as a percentage. We calculate this using the following equation, where we have the actual yield divided by the theoretical yield times with 100. So what is our actual yield? This is the amount of product that can be obtained from a chemical reaction. So typically, if you're in a lab setup, this will be the weight of your final product. And if you are in a test setup or where you're busy doing an assignment, this will be given to you in the problem statement. The theoretical yield is the maximum amount of product that can be obtained from a chemical reaction. This is based on the stoichiometry of the balanced equation and the limiting reagent. So why is this important? Well, the percentage yield is important during the manufacturing of products. So this can indicate how efficient and economical a chemical process is. It can also help us to identify problems in the chemical process, such as incomplete conversions, side reactions, or if purification methods aren't up to standard, and they can help us to improve our chemical process to get a higher percentage yield. So we have 5 main steps to calculate the percentage yield. So first we go and make sure that the the equation that is given to us or that we have to go find is balanced. We need to identify what's in this reaction equation is actually reagents. From the reagents, we determine the limiting reagent, next the theoretical yield, and then finally from the theoretical yield and the actual yield, we calculate the percentage yield. So the first step, we need to balance the equation. So sometimes they are very kind and they give us an equation that is already balanced. On the other hand, we also get that equations aren't balanced. But a good rule of thumb is always to just do a quick check to see if the reaction equation is balanced, if this is not specified in the problem that you get. Next, we need to identify the reagents, and this isn't always as straightforward. I have seen students struggle with this in the lab setting sometimes. So we have 3 cases. We have reaction equations where no solvents or catalysts are added, like the following equation. For example, potassium chloride is added to sodium nitrate to give us potassium nitrate and sodium chloride. On the other hand, we can also get that solvents and catalysts are added to the equation. For example, the synthesis of benzoin from benzaldehyde. Here we have the catalyst and the solvent added just above and below the arrows. Next, we have multi-step reactions. So these are sometimes make it a bit difficult to identify because it's easy to get confused when there is more than one reaction equation to take into account. Once we have identified our reagents, we can go and determine their limiting reagent. So how's this done? This is done by calculating the mole of all the reagents that we have identified previously and determine the smallest one-to-one ratio of these moles. So we have 2 main types of reagents. We have solid-state reagents, and calculating the mole value of the solid-state reagent is pretty straightforward. We just divide the given mass or the mass that you weighed divided by the molar mass, which you calculate. And So remember how we calculate the molar mass. The molar mass is calculated by adding the molar masses of each element in this substance in the ratio of that element in the substance. Now, one place where I have seen students sometimes struggle. So, for example, we have a substance like copper sulfate. So we have copper sulfate, but we have water of crystallization surrounding this crystal. Now, many students make the error of just calculating this molar mass. However, we need to add 5 times the molar mass of water to this, because these water molecules that surround the copper sulfate, they surround it and they add to the mass. Second, we get aqueous solutions. So determining the number of moles of aqueous solutions, just takes a little bit longer. So typically we are given the density if you are in a test environment, but if you are in a lab environment or doing a assignment, you may be able to Google the density if it is not given somewhere. And then from the density, we can go and calculate the mass, which is just the density times the volume. And then this mass we can substitute into the previous equation for calculating the number of moles. So next, we need to calculate the theoretical yield. This is done from the limiting reagent mole. So now we went and we determined which reagent is the limiting one, and we calculate the product mole from that using the balanced equation. So the moles of the product is equal to X times the moles of the limiting reagent, and this X is just simply the ratio in which we find it in the balanced equation. From this number of moles, we can go and calculate the theoretical mass, and that is just the molar mass of the product times with the mole number of the product that we just calculated. So from this, we can go and calculate the yield, the percentage yield. We do that by taking the actual yield and dividing it by the theoretical yield as mentioned earlier and timesing it with 100. So pretty straightforward, and if we follow these steps, we can easily calculate the percentage yield. Let's go and take a look at 3 examples. So the examples that we are looking at are the examples that I used to describe the step for determining the reagents. And for convenience sake, all of them are already balanced, but we are going to follow the steps like previously stated. So first off, we have 8.5 grams of sodium nitrate and 7.5 grams of potassium chloride, which is dissolved in water and allowed to react. And then we prepared 8.135 grams of the potassium nitrate, and we need to calculate the percentage yield. So now we just simply go through our steps. So step 1 was to check that the equation is balanced. So for convenience sake, this was already balanced. Step 2 is to go and determine what are our reagents. So our reagents are just the potassium chloride and the sodium nitrate. Now that we have determined what our reagents are, we can go and calculate the limiting mole. So we can start with the sodium nitrate. So the molar mass of the sodium nitrate, let's just NaNO3, was previously calculated to be 84.995 grams per mole. And now simply we just go and calculate the number of moles. So that is N is equal to M over MR. And we have 8.5 grams. And we divide that by 84.995 grams per mole. And this gives us a mole amount of 0.100 moles. Next, we go and calculate the same for the potassium chloride. So for the potassium chloride, the molar mass was previously calculated as 74.551 grams per mole. And by simply taking the 7.5 grams that we have and dividing that by the molar mass of 74.551 grams per mole, we get a number of moles of 0.101 moles. Okay. Now we can see that these number of moles are pretty close to each other, but a good rule of thumb is always to take the one with the smallest number of moles just in case. So therefore, our limiting reagent is the sodium nitrate with a number of moles of 0.100 mole. Okay, now that we have the limiting reagent, we can go and calculate the theoretical yield. Now, first off, okay, sorry, let me just sodium nitrate, just transfer this here. So the sodium nitrate is 0.100 moles. The first step to calculating the theoretical yield, we need to go and see what ratio these two, the reagent to the product that we have. And in this equation, we have 1 to 1. So the number of moles of the potassium nitrate is simply 0.100 mole. The molar mass of the potassium nitrate was previously calculated to be 101.103 grams per mole. And now to go and calculate the mass, we take the number of moles times with the molar mass. So that is simply 0.100 moles. We times that with 101.103 grams per mole. And we get a theoretical yield of 10.111 grams. Now from this, we simply take the actual yield or the M experimental and divide it by this M theoretical and times it with 100. So they told us that we have 8.135 grams. So 8.135 grams divided by 10.111 grams. And we times that with 100. And we get a percentage yield of 80.46%. Next, we are going to look at this example of the synthesis of benzoin. So they tell us that we have 2 grams of potassium cyanide, which is dissolved in 95% ethanol. And to this is added 10 milliliters of benzaldehyde with a density of 1.04 grams per milliliter and 8 milliliters of water, and this is allowed to react. So if we prepare 7.745 grams of benzoin, we need to calculate the percentage yield. Okay. Step 1, always check to see if we have a balanced equation. And for convenience sake, this equation was already balanced. Step 2, we need to go and identify our reagents. So this would simply be the benzaldehyde because the potassium cyanide is a catalyst and the ethanol is a solvent. So potassium cyanide is a catalyst and ethanol is a solvent. So benzaldehyde is the limiting reagent because it is the only reagent. Okay. So now we need to go and calculate the number of moles of the benzaldehyde that we have, but we do not have a mass. So we need to go and calculate the mass from the density. So we have density is equals to mass over volume. So mass is then density times volume. So this is 1.04 grams per milliliter multiplied with 10 milliliters. And this simply gives us 10.4 grams. Next, we need to go and calculate the number of moles from this. And for that, we need the molar mass of the benzaldehyde, which was previously calculated to be 106.124 grams per mole. So the mole is just 10.4 grams divided by 106.124 grams per mole. And this gives us a mole value of 0.098 moles. The next step is to now go and determine how many moles of the benzoin we have. Well, if we take the balanced equation, we see that 2 benzaldehyde give us 1 benzoin. Therefore, the N of the benzoin is equal to half the N of the benzaldehyde. And this gives us a value of 0.049 moles. So N of benzoin is equal to 0.049 moles. Now we just need to go and calculate the theoretical mass from the molar mass of benzoin, which was calculated to be 212.248 grams per mole. And the theoretical mass is then simply the moles multiplied with the molar mass. That's 0.049 moles times 212.248 grams per mole and this gives us 10.4 grams. Now we have prepared 7.745 grams of benzoin, and from this we need to calculate our percentage yield. So percentage yield is equal to M experimental divided by M theoretical multiplied with 100, and this is 7.745 grams divided by 10.4 grams multiplied with 100, and this gives us a percentage yield of 74.47%. Easy enough. Now for the last example, and this one is going to be a bit longer. So we have 10 milliliters of a 1:1 acetic acid anhydride acetic acid mixture. They give us the acetic acid anhydride density, which is 1.08 grams per milliliter, and 5 milliliters of aniline with a density of 1.3 grams per milliliter, and these were allowed to react. So the resulting acetanilide was then allowed to react with 4 milliliters of fuming nitric acid, which has a density of 1.6 grams per milliliter, to produce p-nitroacetanilide. So if we synthesize 9.4 grams of this p-nitroacetanilide, we need to calculate the percentage yield. So step 1 is always to check that our equation is balanced. For convenience sake, this equation was already balanced beforehand. Now we need to go and identify our reagents. So what are our reagents? Well, the aniline, the acetic acid anhydride, because the acetic acid is a catalyst. And then we also have fuming nitric acid. Okay, so we have 3 reagents. Now we need to go and calculate the limiting reagent. And this is done by calculating the moles of each and then comparing it to see which one has the smallest 1:1 ratio. So let's start with the acetic acid anhydride. But now we have a little extra step here because we have a 1:1 acetic acid anhydride and acetic acid mixture. So this is a 50-50% mixture, and we have 10 milliliters of this mixture. So if it's a 50-50 mixture, we have 5 milliliters of acetic acid anhydride and 5 milliliters of acetic acid. So let's just note that here we have 5 milliliters of this. Because we are working with aqueous solutions, we need to use the density to calculate a mole and a mass, and then we calculate the mole from that. So let's start with the acetic acid anhydride. I'm just going to call this AAA. So from the density, which is mass over volume, we calculate the mass by taking the density times the volume, and that is just simply 1.08 grams per milliliter multiplied with 5 milliliters, and this gives us a mass of 5.4 grams. Now to calculate the moles, we need the molar mass, and for the acetic acid anhydride, it was calculated to be 102.089 grams per mole. So the number of moles is then simply the mass divided by the molar mass, which gives us 5.4 grams divided by 102.089 grams per mole. And this gives us a mole value of 0.053 grams. Let's next move on to the aniline. So we have 5 milliliters of the aniline at a density of 1.03. So aniline, 5 milliliters at a density of 1.03 grams per milliliter. And then we use this to calculate a mass. So density is mass divided by volume. Therefore, the mass is volume times density. And this gives us 1.03 grams per mole multiplied with 5 milliliters. And this gives us a mass of 5.15 grams. Therefore, the mole is then the mass divided by the molar mass. The molar mass was calculated as 93.129 grams per mole. So if we divide 5.15 grams by 93.129 grams per mole, we get a mole value of 0.055 mole. Lastly, we have the fuming nitric acid. We had 4 milliliters of that at a density of 1.6 grams per milliliter. So this is 4 milliliters at 1.6 grams per milliliter. So the mass is equal to the density times the volume. This gives us 1.6 grams per milliliter multiplied with 4 milliliters, which gives us 6.4 grams. The molar mass of the fuming nitric acid is calculated to be 63.013 grams per mole. And this gives us a mole amount of 6.4 grams divided by 63.013 grams per mole. And that gives us 0.102 moles. So now, comparing the mole values, we have that aniline is a smaller mole value than fuming nitric acid, and that the acetic acid anhydride is the smallest mole value at 0.053. So now we go and calculate. So the limiting reagent is the acetic acid anhydride with a mole of 0.053. From this, we go and calculate the mole of the product. So going back to the reaction equation, we see that 1 mole reacts with 1 mole to give 1 mole of acetanilide, and then 1 mole of the acetanilide reacts with 1 mole of the fuming nitric acid to give us 1 mole of p-nitroacetanilide. So the mole of the p-nitro, just going to write it like this is 0.053. Now we need to go and calculate the theoretical mass. So the molar mass for the p-nitroacetanoide was calculated to be 180.16 grams per mole. This gives us a theoretical mass of 0.053 multiplied with 180.16 grams per mole. And this gives us a mass of 9.548 grams. Now to calculate the percentage yield, we take the experimental mass, divide this by the theoretical mass, and we times this with 100. Now we must just go and see, we produced 9.4 grams of the product, 9.4 grams, divided by 9.548 grams times with 100. And this gives us a percentage yield of 98.45%. So see, following these steps, we can easily calculate the percentage yield. So to quickly summarize the 5 steps, we first balance the equation. Even if the equation is given to us, if they do not state that it is balanced, we should always double check just to make sure. Then we need to go and identify the reagents, and remember that catalysts and solvents tend to be given above and below the reaction arrows. From these identified reagents, we go and determine the limiting reagent by calculating the number of moles of each of the reagents and comparing them to see which one has the smallest 1-to-1 mole ratio. From this, we go and calculate a theoretical yield by determining the number of moles of the product that we can produce. And from this theoretical yield and the experimental yield, we can go and calculate a percentage yield. Thank you for watching. Please like this video if it was helpful and share it with your friends and classmates. Also consider subscribing. Bye.